Hi everyone, this is Mrs. G, and today we're going to talk about a new concept, which is the limit of a function. Alright, I have a quick warm-up for you guys. So see if you can graph this function without using a graphing calculator. Just go ahead and pause the video and give it a try. Alright, go ahead and check your work here. Notice I gave this into doing long division. First, if you do long division, you'll see that your remainder is 0, which means that x minus 2 is a factor. So that means that x minus 2 is a removable discontinuity, which would cause a hole at x equals 2. So here's the remaining polynomial, which is just a quadratic equation, which we can graph here. However, we have to take into account that hole at x equals 2. So you simply substitute x equals 2 into the remaining function, and you see that the hole will be at 2, negative 1, which is right here in our graph. So the main focus of today's lesson is just kind of the general concept of the limit of a function. So let's consider some function, f of x. So let's see, this red graph is f of x. As x gets closer and closer to some value, we'll call a, but does not equal a. So everything really, really close to it on either side, but not quite equal to a. The y value that the function approaches is called the limit. So this is the limit of f of x as x approaches a would equal whatever that y value is, L. So notice here, as I'm getting really close to a from, again, the left or the right of our function, we can see that it's approaching this value, which is L. So this concept of that limit is what we're going to be talking about today. So one really important thing I want to highlight from the last slide is maybe you noticed that when we were finding the limit as x approaches a of a function, we said that we were looking to see what happens when it gets really close to a but not equal to a. So when we're finding a limit, we actually don't even care what happens when x is equal to a. We just want to know what your graph is approaching as you get really, really close to x equals a. So let's take a look at these three graphs, and we're going to find the limit as x approaches 2 of these three functions. So in this first graph, we have this parabola. So as x approaches 2, I can see that my graph is getting really close to this point, and the value of that point is negative 1. So we'd say the limit of f of x as x approaches 2 is negative 1. Now let's look at this graph. So it has that same parabola shape, but here you'll notice that there's a hole in the graph when x is 2, and our graph is actually defined at x is 2 right here at 2, 1. Now, as we said up here, it doesn't actually matter what's happening when x equals 2. It matters what's happening when x is getting really, really, really close to 2. So although our function is defined here at 2, positive 1, our limit as x approaches 2 is still going to be here at negative 1. So again, we're looking at what your graph is getting really close to, but not what your graph is when x is 2. Now let's look at this third example. So you can see here, it's very similar to the second one. We have that hole, but our graph isn't even defined at x equals 2. This is actually the function from the warm-up. So can a limit still exist when at a point when your function isn't even defined there? And the answer is yes. So again, we're really just looking at what value is your graph approaching when x is equal to 2. And again, it doesn't matter what it is when x is equal to 2. It doesn't even need to exist when x equals 2. Our limit here would still be negative 1. So just keep that in mind. We're not actually looking at when x is equal to a. We want to know what's happening when x is getting really, really close to a. Okay, so now we're going to talk about this concept of one-sided limits. So here we can describe a limit from two different sides. We can describe the limit as x approaches a, and then you'll see here it kind of has a little minus sign here. This means from the left, or from values that are less than a. So this is the limit of f of x as x approaches a from the left. And then here we have the limit as x approaches a from the right of f of x. So when you see a little plus sign, it means from values that are larger than a, which would be from the right. So we can actually define just one side of our limits. So we can define them individually rather than defining an overall limit. So let's look at this graph here as an example. So you can see that something different is happening as x approaches 2 from the left and from the right. So if we have the limit as x approaches 2 from the left, so here's x equals 2, so I'm going to approach it from the left side. I can see that my y value here is at -1. But if you look at what's happening as x approaches 2 from the right side, so from this little, with the plus sign means from the right, we can see that our graph is approaching +1. So again, you'll notice here our graph is actually not even defined at x equals 2. It doesn't matter, we can still define those one-sided limits. Now, let's talk about the overall limit as x approaches 2 of f of x. You'll notice that the limit from the left-hand side is different from the limit from the right-hand side. So if this is the case, then we actually say that the overall limit does not exist. So this brings up an extremely important concept when we're talking about limits. The limit of f of x as x approaches a equals L if and only if the limit as x approaches from the left equals L and the limit as x approaches right from the right equals L. So the one-sided limits need to match for the overall limit to exist. So that's extremely important to know when we are defining the limit of a function, and it's very possible for a limit to not exist. Okay, so now let's try an example together. We're going to look at this graph of h of x and see if we can state these following values. So for the first one, they're asking us to find the limit as x approaches -4 from the left. So here's -4, and as I approach from the left, I can see that the y value is approaching +2. Now let's do the limit as x approaches -4 from the right. So again, here's my graph. I'm going to approach -4 from the right, and our graph is also approaching 2. So if we want to find the limit as x approaches -4, the overall limit, since the limit as it approaches from the left is the same as when it approaches from the right, that will be our overall limit. So it is also 2. Again, it doesn't matter that our graph is actually not defined at x equals -4, because we're just worried about what happens as we get really close to -4. All right, let's try finding the limit as x approaches 1 from the left. So here's me approaching from the left, and I could see that my graph is approaching y equals 4. And then if I look at, sorry, this was supposed to say 1 from the right. As x approaches 1 from the right, I'm going to trace my graph like this. I can see that my graph is approaching y equals -2. So here you'll notice that the limit from the left is different from the limit from the right. So that means the limit as x approaches 1 does not exist. Again, because the left-sided limit does not equal right-sided limit. All right, let's look at these last few. So the limit as x approaches 6 from the left. Again, I'm going to trace my graph. And as I approach 6, my y value is approaching 5. And then I'm going to see what happens as I approach 6 from the right. So here's from the right, I'm going to start approaching 6. My graph is also approaching 5. So even though my graph doesn't exists at another point at 6, 2, as x approaches 6, my graph h of x is approaching 5. So that is the limit as x approaches 6. All right, so next we're going to talk about this idea of what's called an infinite limit. So consider a function f of x. So same scenario as x gets closer and closer to a, but does not equal a, and the y value increases or decreases without bound. So this essentially just means that your graph is going to head towards positive or negative infinity. Then we can describe the end behavior in the following way with a limit. We can say the limit as x approaches a of f of x equals positive infinity, so that would be increasing without bound, or we could say the limit as x approaches a of f of x equals negative infinity, so that would be decreasing without bound, so going down and down forever. Now here's the thing, you'll notice that in the title, the word limits is in quotation marks. That is because, well, infinity is not really a value. So the actual limit, technically it doesn't exist, right? So again, infinity is not a value, so how can you approach something that isn't a value? However, when we state these limits, where this is a way of describing why the limit does not exist. We can still describe the limit. So if I asked you for an infinite limit, you could still describe it as positive or negative infinity, but it's just important to know that, again, infinity is not a real value, so technically it's not actually approaching a real limit. And this leads us to the technical definition of a vertical asymptote. So the vertical line x equals a is a vertical asymptote of f of x if at least one of the following statements is true. So you'll notice here that we have the limit as x approaches a either from the left, right, or from both sides. It can be infinity or negative infinity. So if you have one of these scenarios, again, approaching a value from the left or right and either going up without bound or down without bound, then we can say that that value a is a vertical asymptote. And maybe you remember describing asymptote behavior in a previous class. Really what you were doing is describing an infinite limit. All right, so let's try another example together. So here we have the graph of g of x, and we're going to try to find the following values if they exist. So first, let's find the limit as x approaches negative 1 from the left. So here's negative 1. You can see that we have a vertical asymptote here. And as I approach it from the left, you'll see that my pointer starts going up and up and up. So it's increasing without bound. So that means that g of x will approach positive infinity. And if I approach negative 1 from the right, so again, I'm here and you notice my pointer is going down infinitely. So my graph is going to approach negative infinity. So here, next we're asked to find the overall limit as x approaches negative 1. So you'll notice again, the left-sided limit does not match the right-sided limit. One side is going up, one side is going down. So we'll say that the limit as x approaches negative 1 does not exist. They do need to match for us to be able to describe that overall limit. Now let's look at the D, E, and F. So this is the limit as x approaches 2, first from the left. So from the left, you can see that our graph is going down infinitely, so it will approach negative infinity. And from the right, so I'm going like this, it's decreasing without bound, so it also approaches negative infinity. And you'll notice that since our graph is approaching negative infinity from the left and the right side, it matches, then we could say that the overall limit as x approaches 2 of g of x is negative infinity. So we will still want to describe this overall limit, but again, the left and the right side need to match. All right, so I have one for you to try on your own. Here's a graph of f of x and see if you can state the following limits if they exist. All right, go ahead and check your work here. Just a couple to watch out for. Again, as x approaches negative 6, you'll see the left-handed and the right-handed limits are not the same, so the overall limit does not exist. Same thing will happen at x equals 3. This would be considered a vertical asymptote, but since the left and right side do not match, the overall limit again does not exist. But at x equals 8, this asymptote, this vertical asymptote, you'll see that both sides approach negative infinity, so the overall limit is also negative infinity. All right, so next we're going to talk about a couple of very basic ways that we can try to evaluate limits of functions. So the first way is to evaluate a limit graphically. So you may not just be given a graph like we were in the previous example, so you may need to graph it yourself by hand, or maybe you can use a graphing calculator to help, and then you can look at the graph and see if you can evaluate the limit from what you have graphed. So let's look at this rational function right here. Let's try to graph this without a graphing calculator just for practice. So the first thing we're going to want to do is factor the denominator. And you'll see here that we do have a removable discontinuity. That x minus 3 factor cancels out, which means that we are going to have a hole at x equals 3. All right, and to find the coordinate of that hole, we can substitute 3 into our remaining function, and we see that the hole will be at 3 1/5. We can also see that since we have this remaining factor in our denominator, that we're going to have a vertical asymptote at x equals -2. And then if we evaluate the degree, the difference in the degree between the numerator and denominator, since the degree is larger in the denominator, our graph is going to approach 0 as x approaches positive or negative infinity. So we have a horizontal asymptote at y equals 0. So here we can plot the coordinate of our hole, so 3 1/5. And if we want, we could find a couple more key points. For example, we know that f of 0 would be 1/2 if I plug it in here. So we have a graph that looks like this, and here's just a little rough sketch. And then if you plug in any point that is left of -2 or less than -2, the y value is going to be negative because our denominator will be negative. So I know that the rest of our graph, again, a really rough sketch here, will look something like this. But I know it's going to be below our horizontal asymptote. So now looking at our graph, I think that we will be able to evaluate these different limits. So first, the limit as x approaches -2 from the left. So you can see here's our vertical asymptote at -2, and as I approach from the left, my graph is going down, so it approaches negative infinity. But as it approaches -2 from the right, you can see that my graph is going up, so it approaches positive infinity. And since the left-handed and the right-handed limits do not match, the overall limit as x approaches -2 does not exist. Now let's look at what happens as x approaches 3 from the left. So as x approaches 3 from the left, I see that I am approaching that value of 1/5. And same thing as I approach from the right. So even though our graph is not defined at x equals 3, the limit still exists because the left and the right-handed limits are the same. So our overall limit is 1/5. So you can see that we can sometimes evaluate a function, the limit of a function graphically. Sometimes it works really well depending on how complex the graph is. Sometimes it actually is pretty difficult to see what the limit is. So we will learn other ways later on in this unit. All right, so I have one for you to try on your own. See if you can evaluate the following limits graphically. All right, go ahead and check your work here. So remember, when you're graphing piecewise functions, you are going to want to evaluate each part of your function at those kind of crossover points, even if it doesn't exist there. So I did plug in -2 into this first part of my function to find this part, to find this coordinate, and then I followed the slope going to the left. But even though this part of my function isn't defined at -2, I'm still going to plug it in to see where I should put my open hole. Same thing at 6. It's not defined at 6, but you should still plug it in to see where that coordinate would be, and then it's a linear function between those two. Our graph is defined at x equals 6 at 5, so that's just a single coordinate, and then to the right of 6, it's simply a quadratic function, and the vertex is actually at 6, -4, so at that coordinate. So here you can see that as x approaches -2, the left and the right sided limits are not the same, so the overall limit does not exist. But as x approaches 6 from the left and right, the limits are the same, so the overall limit does exist. So the next strategy we're going to try for evaluating the limit of a function is actually using a table of values. So here we're trying to find the limit as x approaches 1 of this function. We could graph it and see, but let's try with a table of values. So I'm going to actually put this into our graphing calculator, and we can actually have it do the table of values for us. So the first thing you're going to want to do is you're going to want to input this function into where it says y equals. And then we can actually just use the table function, and it will evaluate whatever x values we want. So a little faster than us plugging it in by hand. So one thing you're going to want to make sure, you're going to want to go to second table set and make sure you change the independent variable to ask. So that means that we can plug in whichever x values we want, and then in the table it will tell us the y values. So then once you've set it to this, if you go to second table, we can start inputting our different x values. So since we want the limit as x approaches 1, we can pick a couple values to the left of 1, but really close, and then a couple values to the right of 1. So let's just get a little bit closer and closer. Let's try like 0.5, and then we could try 0.9, and let's try 0.99, and let's even try 0.999 and see what we get. So here's the values that I got from my graphing calculator. Again, these are just values as x approaches 1 from the left, so I'm getting really close to 1. So let's try a couple from the right. So maybe we'll kind of work our way down. We say 1.5, 1.1, 1.01, 1.001. We could get even closer and closer if we wanted to, but go ahead and plug those in and see what you get. All right, and here's the values that I got from my graphing calculator again. So you'll see that as we approach 1 from the left or from the right, our values are getting closer and closer to 0.5. They're actually really, really close. And you could even go a couple more decimal places with your x values if you want. But I'd say that this is a pretty good estimate. We could see that these values are approaching 0.5. So I'm going to estimate that the limit as x approaches 1 is 0.5. All right, so now we're going to talk about some of the potential pitfalls that you might come across when using this strategy to evaluate the limit. So the first is that our calculator will have limitations of what it can do, especially in terms of how many decimal points it can handle. So for this function here, if you plug this function in your calculator and you start plugging in some points that are really, really close to 0, here's what you'll see. So if you plug in 0.01, you get 1,666.7, and if you plug in 0.001, you get 166,667. So you can see that's getting really, really large, really fast. The next value it says is 1.67, and then you'll see this E7, which means times 10 to the power of 7, scientific notation, and then 1.67E9. So you can see that these values are extremely, extremely large. But let's say you really wanted to be sure. It looks like our graph is approaching infinity, which it is, but let's say you plug in this next value. When you do this, your calculator is going to say 0. So what's happening is it's not actually approaching 0. The problem is that our calculator can't actually handle this many decimal points out for this function. So if you start using values that are too small or values that your calculator can't handle, you might get some misinformation that would lead you to the wrong conclusion. So here we can see our graph is approaching positive infinity as x approaches 0. However, again, just if you went a little bit too far with the decimal points, your graph will tell you 0, which is just not true. It's just that your calculator can't handle it. Another value or problem that we may come across is that we might pick inappropriate values unintentionally, and that might lead us to the wrong answer. So let's consider this function, sine of pi over x, and we want the limit as x approaches 0. So let's say again, I put this in my calculator and I start trying these numbers. So these first three would be really logical choices to make. And if I do that, if I plug in 0.001, I get 0. And if I plug in 0.001, I get 0. And if I plug in 0.0001, I get 0. So I'm probably thinking, all right, my graph is approaching 0. But let's try some other decimals that are getting increasingly close to 0. And actually, I'm going to change this one. This was a little typo. Let's just try 0.4. So if you plug in 0.4 into your calculator, you actually get the result of 1. And then let's try another smaller value, 0.0198. So if you plug in that decimal, you actually get 0.99986. 7. So all of a sudden you have some values that seem like maybe they're approaching 1 instead of 0, depending on where they are. So for this graph, if you actually look at the graphing feature in your calculator, you see something really weird happening as x approaches 0. It actually starts oscillating between +1 and -1 infinitely. So it never really approaches either one as x approaches 0. It's kind of just, again, oscillating between +1 and -1. Now, if you didn't look at the graph, or if you were just doing this method, this seems like a very logical answer. It seems like it should be 0. Or maybe if you're picking other, inappropriate values, maybe it seems like your graph is approaching 1. But it's actually not approaching either. This limit actually does not exist. So this is really, something you might not see if you're using this strategy. So again, sometimes the strategy of using a table of values works really well to evaluate a limit, but sometimes it just doesn't. So again, that's why we are going to learn a few more accurate methods later on in this unit. But for today, it's definitely a good way to introduce ourselves to this idea of limits and how to find them. All right, so I have one last problem for you to try on your own. It kind of ties together everything we talked about today. So pause the video and give it a shot. All right, so go ahead and check your work. Your graph doesn't need to look exactly the same as mine, but it should have a few of these key characteristics. So here you should have your limit approaching +3 from the left and -1 from the right. One of them should be closed or one should be open, or they can both be open, but just make sure they're not both closed because they can exist at both points at the same time. And then since the limit as x approaches 1 is 0, but f of 1 is equal to 4, that means there must actually be a hole at 1, 0, and your graph is going to go through. And then last, since the limit as x approaches 3 of our function is infinity, that means from the left and right, our graph is going to go up. So it should look something like this around that, what is a vertical asymptote at x equals +3. All right, so that is all for today's video. Thank you so much for watching.